to our next talk. So this talk will be given by Professor Chelsea Flynn. So Chelsea has done like a bachelor in MIT, and then her PhD in UC Berkeley, and now she is an assistant professor in Stanford University. So she has been focusing on meta learning and multitask learning. So especially to apply this to large scale and also to multiple applications like to vision, machine learning, and robotics. So yeah, it's very exciting to have her here. And one thing I want to mention that she has a very exciting course about meta learning and multitask learning. So if you are interested in this topic, that is definitely one central place that we can get started. So yeah, welcome, Chelsea. So the time is yours. We are looking forward to your talk.
Great, thank you very much for the introduction. So a lot of my motivation for multitask learning comes from actually studying robotics, where we, at least in terms of building robots that can do things, we ultimately often want them not to do one very particular thing, but we want them to be able to do lots of things for us. And in my research, I'm really fascinated by the question of how robots might be able to develop broadly intelligent behavior through learning and interaction. Now, it turns out that oftentimes when you do move from a very single task learning paradigm to a multitask learning paradigm, there are a number of challenges that arise. And in a lot of my talk, I won't actually be focusing on robotics, but I'll be focusing on some of the challenges that arise and trying to understand specifically how transfer occurs in multitask learning and whether we can control that transfer in order to improve learning of multiple tasks. And so in particular, I'll have three parts. First, we'll be looking at the transfer of invariance across tasks and seeing how we can control the transfer of invariances through different mechanisms. Then I'll talk about, can we control transfer instead by selecting which tasks we'll be training together? And then lastly, I'll be talking about how we might be able to move towards zero-shot generalization to new tasks. And so all of this will be kind of around this central theme of trying to understand and control transfer in multitask learning. So now let's first start by talking about the transfer of invariances. Our motivation for this is that long-tail distributions are pervasive in a lot of applications of machine learning, where you have some part of your distribution has a very large number of data points, and a very large part of your distribution has only a small number of data. And this could be over categories, it could be over lots of different things, it could also be over tasks, for example. And in particular, we know that a lot of machine learning models do very poorly on the tail of the distribution, and we'd like to understand why these models do so poorly and ultimately try to have them do better on the parts of the distribution in which there is a small amount of data. And when thinking about this, we formulated this hypothesis, which is that we think that models will fail on the tail of the distribution because they're failing to transfer invariances from the head to the tail. And what I mean by that is that oftentimes there are things in an image, for example, that you want to be invariant to, like lighting, like background, that sort of thing, depending on the task. When you have a lot of data, you can learn those invariances implicitly. You can learn that the background doesn't matter for the task. However, when you have less data, you won't necessarily learn those things, and you'll ultimately potentially fail to solve the task. Now, if you have a long tail distribution, ideally the model would automatically learn the invariances from the head of the distribution and then transfer that to the tail classes. However, if this transfer isn't actually automatically occurring, then this would lead to poor generalization on the tail and lead to poor performance on the tasks or the categories in which we have less data. Now, one of the cool things about this hypothesis is that we can actually explicitly test it. So what we did is we took these are going to be fairly synthetic experiments, but later we'll move on to some more realistic data sets and so forth. But what we're going to do is we're going to create a synthetic long tail data set with invariance to a particular known transformation T. And then we can train models on that long tail data set and evaluate their invariance to T on different parts of the distribution. And so in particular, we take the K49 data set, which is a data set of 49 different Japanese characters, and we create we consider different transformations, like changing the background shading, for example. And we can then create a long tail distribution with these 49 characters and also kind of augment the background. And importantly, we're going to do the augmentation before we create the long tail shape of it, so that this part of the distribution in the tail doesn't have a lot of data of this invariance. We'll likewise do this for other invariances like image dilation and erosion or rotation of the digit. And so I'll be from the K49 data set. Great. And so what we're going to do is we're going to measure the invariance to this transformation with respect to the class size. And in particular, the way that we're going to measure invariance is we will take the original image, then we will transform it with our function t and measure whether or not the predicted labels agree or not. And so in particular, we're going to measure the KL divergence between the model's predictions on the original data point and the model's predictions on the augmented data point when it's transformed by t. We're going to measure this invariance as a function of the number of examples per classes. And if it is transferring invariances across classes, then we would expect to see kind of a very horizontal line. Whereas if it is not, then we would expect it to have worse invariance or a higher number for the small number of examples and the lower number for the large number of examples. And we see exactly that latter trend, where when you have a lot of data, the model is accurately able to be invariant to this transformation. Whereas when you're in parts of the distribution that have a very small number of examples per class, it isn't invariant to these transformations. So this suggests that this sort of transfer of invariances isn't happening automatically when you train a neural network on long tail distributions. And if you're curious what the difference between these two lines is, this orange line is doing delayed resampling. And so later on in training, it's actually resampling the data to the uniform distribution. And what this orange line suggests is that even when you resample the data to the uniform distribution and upweight the data points that have a small amount of data or upsample them, you still see this trend where it's not invariant to these transformations when you have small amounts of data. Okay, so invariances are not transferred across classes. Now, a natural question is, can we actually control this transfer? Can we encourage the model to transfer invariances across classes so that it does well on categories where you don't have a lot of data? So we consider like a very simple approach for doing this, and it has a lot of ties with prior work. In particular, we're going to try to train a conditional generative model to estimate the transformation T, to estimate the transformations that preserve the class. This is similar to some previous works that also try to learn these perturbation sets. However, one key difference is that we're not going to assume paired transformation data. We're just going to train a generative model, a conditional generative model on each class to be able to generate images of that same class. And so there might be other things that are varying. And then once we have this generative model, we can use this model to augment our data and create examples that create more data essentially that illustrates that invariance to the model. And there are also related works on using kind of neural networks as data augmenters as well, so I should also mention those. And so as an example of what this might look like is here is kind of some original examples from the data set, and then our generative model we can use to essentially augment those examples and create examples with different backgrounds. And we find that this works both for large classes as well as for the small classes. So importantly, this generative model is able to generalize well to the distribution. And we see the same with this other data set, which is these German traffic signs. Okay, and then now the natural question is, does this actually improve invariance on small classes? Are we explicitly controlling the transfer in this scenario? And so again, we're going to look at invariance versus class size. And what we see is when we use this approach for trying to explicitly transfer invariances, we see this green line right here, which is noticeably more flat than the other lines. And so this suggests that it is actually improving invariance on the small classes. Unfortunately, you might also notice that it's actually worsening the invariance on the well-represented classes. And this is likely because the generative model isn't perfect. And it also just suggests that when we use it to try to improve invariance, we can just apply the augmentation only to the small classes. And that should hopefully allow it to not kind of worsen the performance on settings where you already have a lot of data and you don't need the generative model. And then finally, of course, do these improvements in invariance actually translate into better balanced accuracy? And so we compared this, we applied this generative invariance transfer approach to these prior methods for handling long-tailed distributions. And we see on the K49 dataset, we see a 4 to 10% improvement in balanced accuracy, which is pretty substantial. And on these more realistic data sets on the German traffic signs and CFAR long-tailed versions of these data sets, we see a 1 to 10% improvement here as well. We see the largest improvement on the German traffic signs. We see the smallest improvement on CFAR 100. This is likely because of imperfections in the generative model. And I think that if you had a better generative model and tuned that model better, you would probably be able to get further improvements here. Great, so the takeaway here is that we can actually explicitly encourage the model to transfer invariances across classes, and this allows you to significantly improve performance on tasks or categories where you don't have a lot of data. Great, so in particular, kind of at a higher level, we know that these invariances don't transfer automatically, but we can actually enforce it, and I presented one mechanism that we could try to enforce this kind of transfer. I suspect that there are probably many other mechanisms as well. Great, so now I'd like to transition to kind of thinking about a different way to control transfer in multitask learning. And in particular, we would like to be able to control transfer by selectively identifying which tasks you want to train together. And the motivation for this is that there are a lot of scenarios where you have many different tasks, or maybe you have a lot of different auxiliary tasks. And it's unclear whether you should train on all of them. It's unclear which ones will be complementary. And ideally, we would have a metric that could just tell us automatically whether or not two tasks are complementary and whether it'd be helpful to train on one of them. And unfortunately, there was this nice paper at ICML last year that showed that it's actually fairly unintuitive to figure out which tasks are complementary. They looked at kind of the performance of these different tasks when you train it with these other tasks. And we find that sometimes, like, for example, training depth with semantic segmentation is helpful for depth. Actually hurts depth, but it actually improves semantic segmentation. And there's this kind of weird asymmetric relationship that's actually, at least in my opinion, quite unintuitive, and it isn't something that we would necessarily be able to judge right off the bat. And the challenge here is that task affinities is going to depend on things in the data. It's also going to depend on the model's current knowledge. So for example, if you've already learned how to detect edges, if your model already has that knowledge, then training on two tasks that only have edges in common probably won't be very helpful. Whereas if it hasn't yet learned edges, then training on those two tasks could be helpful because it would help it learn the basics like edges. And then it's also going to ultimately depend on a lot of properties of the optimization process, like the optimizer, the learning rate, the hyperparameters, and so forth. And to give a sense for how difficult of a problem this is, this paper kind of was talking about which tasks should be learned together. And one of the things that it suggested is to just exhaustively search for all combinations of tasks. And this is something that's kind of fairly impractical to do and computationally expensive to essentially try to train on all pairs of tasks. So the bad news is that there's really no closed form solution for measuring task affinity from the data. However, there is something that we can do to try to measure task affinity in an efficient way. And in particular, we're going to try to just approximate these task affinities from one training run of training all the tasks together. And the way this will work is we'll first train all of the tasks together in a single multitask network. Then we're going to analyze this training run and try to compute affinities based on that optimization. Then we'll use these task affinities to select groupings of tasks, and then ultimately train a network for each grouping. Now, the hard part is this second step right here. I think that we know how to train all of the tasks together. We also know if we have these affinity scores, then we can fairly easily figure out what the groupings should be. But actually computing these affinities is difficult. So how do we do step 2? Ideally, what we want to be able to measure is how much training on one task is helpful for another task for a particular model. And what we're going to do is we're going to look at this very simple equation here. And in particular, what this is measuring is it's looking at the parameters of the model after you update on task I. And it's going to look at what the loss is for task J after you do that update. And so this is essentially after you update on task I, how helpful is that for task J? And we'll measure this and compare it to the loss function before any update. And so essentially what this is measuring is whether update on task I is helpful, whether the gradient for task I is helpful for task J. And if this kind of term is small, that means that it is being helpful. And so if you take 1 minus that term, that means that the larger this quantity is, the kind of larger your affinity is, the larger, the more complementary task I is for task J. And so this is an asymmetric metric, which is good because that reflects the fact that tasks often have asymmetric effects on one another. And then what we can do once we have this measure is, this is for a particular model at a particular time, but you can average this metric over different training iterations to essentially get these training level pairwise scores between each pair of tasks. And so this gives us this training level affinity score for different tasks. And then once we have that, we can ultimately use that to determine our groupings of tasks and then train on those groupings. And what we find is if we actually evaluate this approach on both the SLEB dataset as well as the taskonomy dataset, this approach, tag or task affinity groupings, is doing better than more naive approaches that, for example, do fold multitask learning or other simple approaches. And it's also substantially faster than approaches that essentially do more of an exhaustive search over task affinities. And so in particular, it really achieves the same improvements as these prior approaches, but with tens or hundreds of fewer GPU hours. Great, so the takeaway here is that we can essentially automatically select task groupings from a single training run, and this is an efficient and useful approach for controlling how information is transferred across pairs of tasks. Now, the last thing I'd like to talk about is ultimately transferring to new tasks. So far I've talked about controlling transfer when you're given a set of tasks and want to do well in that set of tasks. However, in many situations, we don't really anticipate all of the tasks that we might want our system to be able to do. And we'd like to be able to ultimately be able to do new tasks that, that they weren't explicitly trained to do. And this is, I mean, look at this in the context of robotics, because oftentimes in robotics, we can write down a number of tasks, but ultimately we also want them to be able to generalize to new tasks that they weren't trained to do because we don't know all of the space of tasks ahead of time. Now, it's worth mentioning that there are prior works in this area where works have looked at trying to generalize to new tasks from a human demonstration or from language instructions. These have made kind of progress on this goal. For example, these works on the left can generalize to new objects. However, they're all trained and tested within a single skill, such as placing. And so this limits essentially how broadly it's able to generalize. And then these works on the right, they're able to generalize to new instructions, so new phrases of describing a task. But ultimately, the new instructions in these works are describing behaviors that are seen in the data. And so what we'd like to do in the context of these works is to be able to ultimately perform new behaviors that weren't seen in the data and generalize to those new tasks. And in particular, what I mean by generalizing to a new task is we'd like to be able to say, tell the robot, I want you to place the grapes in the ceramic bowl. And in the data set, it had never seen data of picking up grapes and placing it in a ceramic bowl. It had seen data of placing other objects. It had seen data of doing other things with grapes, but not this particular combination. going even further, it actually never saw the grapes and the ceramic bowl in the same scene before. So we actually collected data with 2 different object sets, and we're going to be asking it to generalize to tasks that involve combinations of objects that weren't ever seen together. And to study this, we're going to collect demonstration data for 100 total tasks that cover 9 different underlying skills. Here's an example of some of the data that we collected. So we collected data through this teleoperation interface that essentially allows a user to control the robot's behavior. And it includes tasks like knocking an object over, like stacking an object on top of another object, picking an object and placing it into a tray, or wiping a surface with a sponge. Now, ultimately, if we want to be able to generalize to new tasks, we need to be able to condition the model in a way that allows it to do that. And if you just condition on like a one-hot vector of the task, then if you give it a new one-hot vector, it won't be able to interpret that and understand what it's supposed to do. And so what we're going to do is we're going to take our diverse data set and we're actually going to condition the policy on either a video of a human doing a task or a language instruction of the task. And by using these kinds of task conditioning mechanisms, this should allow the system to be able to interpret the instruction for a new task, because these kinds of commands are, they're essentially stated in a way that that isn't kind of as discrete as a typical multitask identifier. And yeah, and it's something that ultimately can, if it really semantically understands the instruction, for example, it should be able to generalize to instructions within that space. So the policy is going to operate directly on RGB images. We're going to be doing 10 Hertz 7 DOF position control. This essentially makes the system maximally general. We're also going to be using a fixed pre-trained language encoding. And so when we pass this language into the network, we're not going to actually train directly end-to-end on the language tokens. We're actually just going to use a fixed embedding of that language. And then when we use the video, we're actually going to try to regress the video onto that language representation of the task. And we found that this approach to producing embeddings for the multitask network actually worked substantially better than trying to do end-to-end training. And then ultimately, if we want the robot to generalize to new tasks, it actually has quite a difficult task that it needs to do. It needs to be able to correctly interpret the command. It needs to be able to visually identify the objects that are relevant to that command versus distractor objects. And it also needs to ultimately translate the instruction and the perception into the robot's action space. Okay, and so here's kind of a qualitative example of the task that I showed before, where the robot had never seen grapes or a ceramic bowl in the same scene. It had never seen this instruction before or demonstrations of this behavior. But we see that after training on 100 tasks, the robot is actually able to generalize zero shot to this new task. It's getting a little bit choppy at the end, but hopefully you get the main idea. Here are some qualitative examples of other tasks. So placing a bottle on a tray, pushing a purple bowl across the table, or placing the banana on the white sponge. And we also see that here the robot is able to generalize to these new tasks as well. Great, so quantitatively, we evaluated the performance on 28 holdout tasks. We pre-selected these tasks and evaluated on them. And so we didn't know whether it was going to generalize before we did this evaluation. And this is the performance here. I'm going to focus on language conditioning for now, just for simplicity. And what we find is that we get a non-zero success rate for 20 out of 28 of the holdout tasks. And we get an average of 32% success over the 28 tasks. So really, this shows really substantial signs of zero-shot task generalization, which is pretty exciting. It also shows that there is, of course, considerable room for improvement, which also makes it exciting from the standpoint of future research. One last question we looked at is, where is the room for improvement? I mentioned these 3 different aspects of things that the robot has to do. Which part of the system is the robot struggling? And what we can do is we can evaluate the robot on some of the training tasks, as well as the held out task. The held out task is the same as what's shown here. And what we see is that we see an 8% gap in interpreting the training language versus the language instructions from the training set versus language instructions that are doing held out tasks. And we see only an 8% gap in interpreting the held out language. We also see a 2% gap in interpreting one-hot vectors versus language instructions. And then we see like this pretty large gap just in terms of how well the robot is able to do multitask control from one-hot vectors. And so this indicates that the biggest challenge or the biggest room for improvement here is ultimately on just performing multitask visuomotor control. Great, and then we can also look at some example failure cases. These are two tasks that the robot actually had a 0% success rate on, placing the banana in the ceramic cup and wiping the sponge with the tray. And we see that in both of these cases, the robot is actually able to successfully perform a large portion of the task. It clearly understands what the task is, but in this first case, it didn't quite get the banana into the ceramic cup. It just tried to place it on top and failed at the very last part. And likewise, in terms of wiping a tray with a sponge, the robot very nearly performed the task, but didn't quite actually finish performing the wiping motion. So really, it seems like this really fine-grained control of the system, really not the perception part and not the task identification part, is really the bottleneck for getting good performance. Great. So the final takeaway here is that we can enable zero-shot transfer to new tasks if we give something like a language instruction to the model. And so to wrap up, I talked about this kind of general goal of understanding and controlling transfer and multitask learning. I talked about how invariances don't transfer automatically, but we can enforce their transfer. I talked about how we can also enforce transfer by selecting task groupings, and we can do this efficiently from a single training run. And then I lastly talked about transfer to new tasks through these language embeddings. And overall, I think that understanding transfer and trying to harness transfer and control it in certain ways is ultimately a powerful tool for better multitask learning. I'd like to thank my students and happy to take a couple of questions.
Yeah, thank you. Thank you for the excellent talk. So are there any questions? Yeah, maybe I can start with one. So for the first work you mentioned that you want to learn some, let's say, category preserving feature transformation to augment the data. Can you actually like elaborate a bit more? How do you control like this transformation actually can preserve the category, I mean, without violating the semantic category constraint?
Yeah, so we tried a few different approaches for doing that. One approach that we tried was to essentially train a conditional GAN that is where the discriminator is discriminating between whether or not two images are from the same class or not. And then you try to trick that discriminator into thinking that the generated image is from the same class as the image that it's being conditioned on. That's one approach that we tried. We also tried simply training this kind of an existing model that's explicitly trying to kind of separate content from style. And we just train a GAN conditioned on an image, but just the discriminator just is a standard discriminator. We actually found the second to work better. And so there's essentially an inductive bias in the generative model that encourages it to kind of more change the style of the image rather than the content of the image. But I think that the former approach is also makes a lot of sense as well.
Yeah, that's good. There's also one question from the chat, so maybe I can read so that we can also record this in the video. So, okay, the question is that whether you could actually share some more insight on the task affinity scores, like how do they change with the training duration, and to what degree do they depend on the size of data set used to train the multitask learning net?
Yeah, so I'd encourage you to take a look at the paper for more kind of for more kind of information on that. We actually had a lot of visualizations in the paper and a lot of analysis on these affinity scores. We actually found that interestingly, they do actually change during the training duration. And that was something that I found pretty interesting. And I think that in the paper, we actually had a plot that showed this changing. I think it was in the appendix of the paper. Another thing that we found is that it actually also depends on things like the hyperparameters of the network, for example, like the hyperparameters of the optimization run, like the learning rate. This isn't something that you would necessarily think of as something that should affect task affinity, but we find that actually these kinds of things do actually affect which, we did kind of a quantitative analysis on, like, if you change the learning rate, does that change which tasks you should train together? And we found that it did actually change that. And with like a learning rate that was 2 times the size of another learning rate, the optimal task groupings for the first setting was actually like much worse with that different learning rate. And so this approach can actually account for that by looking at an optimization run when you train the neural networks together with those hyperparameters, and adapt the affinity scores to those hyperparameters essentially.
Yeah, there's a further question regarding this. So, do the retrieved affinity score agree with the previous studies, such as taskonomy?
Yeah, so insofar as it's performing similar to the affinity scores in the taskonomy paper, so HOA is the affinity scores from the taskonomy paper. Insofar as it's doing well, then it is, I think, agreeing probably. I don't have the kind of a confusion matrix of or a correlation matrix between those different scores, but we do see that we're able to perform somewhat similarly, at least in the case where you have like 2 groupings of tasks to those previous affinity scores, while of course being substantially more efficient.
Yeah, are there any more questions? Yeah. Okay, there's a general question about meta-learning. So what is the meaning of the word impressive power of a meta-learning or multitask learning model or multitasking model?
Yeah, so this isn't something that pertains too much to my talk, but one thing I talk about in my meta-learning course, CS330 at Stanford, is talking about the expressive power of a meta-learner, which I used to refer to like the class of learning procedures that it can represent. So for example, if you kind of constrain it to be performing a gradient descent from a particular initialization, but you only allow it to change the learning rate, then that has very little expressive power in terms of the learning procedures that you can represent. Whereas if the learning procedures you can represent are represented by this huge black box neural network that takes as input the data and outputs parameters, that has a lot of expressive power. And so I often use this term to refer to the class of optimizers or the class of learning procedures that you can represent.